Okay, welcome to lecture here. So we're going to continue on chapter 4, I think. So we are going to just lecture a little bit here. We'll stop. And as we talked about last time, the exam will open up around the start of lab time, around 7:15. And you could go and take the exam, obviously, at that point. Again, as we talked about last time, you'll need to take it using proctorial and all that kind of stuff, just like we did pretty much the quiz. And so, like I said, we'll just continue on a little bit here so we don't follow too far behind in terms of material. So we've been talking about in this chapter here geometry, really kind of a continuation, if you will, of the previous chapter where we talked about really drawing Lewis structures. So here at the beginning, we talked about geometry. We talked about really two types of sort of geometry names. One is sometimes referred to again as the electron pair geometry, which is basically the three-dimensional arrangement of the electrons around the central atom. The other name is the molecular geometry, or the shape, and that describes the overall molecule's overall shape, taking into account its bonds, its electrons that are present, and so forth. So as we talked about, in some cases, those names are exactly the same. The electron pair geometry and the molecular geometry name are the same. And those are the cases where when you draw your Lewis structure, you pretty much have no non-bonding electrons around the central atom. So they're all bonding electrons. And in that case, the bonding electrons, the electron pair geometry and the molecular geometry will be the same name. It's only really when you start to introduce non-bonding electrons around the central atom, as we saw, so pretty much dots on your Lewis structure, that you do start to see a difference in the name. And that's because you're getting different types of interactions starting to happen at that point. You're going to be getting bonding electrons near bonding electrons, non-bonding near non-bonding, and bonding near non-bonding electrons. And what happens is, especially the non-bonding and non-bonding electrons, they really don't like to be near each other. So they do try to get away from each other as far as they can. And that ends up sort of making the overall molecule really sort of bend a little bit more than it would if there was still a bond present at that point. So the name that does change is the molecular geometry name. Again, the electron pair geometry name remains the same in that case. We also saw some more geometry than maybe you have seen before, and we see a lot of it in our expanded octet, where we do have 5 electron pairs and 6 electron pairs around the central atom, and those give us some new geometries that, again, in the triangular bipyramidal and the octahedral sort of realm of geometry. Like we talked about again, and as you probably also know, you do just basically have a double bond or a triple bond. Again, in terms of counting for electron pair geometry and molecular geometry, those do count as only 1 electron pair and 1 bond. And you do need to know, obviously, all of those geometries. It will not be provided for you. Any questions on that there? Okay. So what we are going to then continue on with is another type of sort of bonding theory, if you will, and it's what is sometimes referred to as hybridization. And valence bond model basically describes a covalent bond, as we see here, as really an overlapping of those orbitals. So when those orbitals basically come together, there's this region where overlapping of them happen, and that's thought of as where those electrons would be shared between the two atoms. And this sort of orangey region here is where those electrons, again, would sort of be shared, and what would hold that bond together here. And we would get our covalently bonded H2. Now, what happens when we sort of look at sort of geometry and the angles that we saw when we talked about the geometry, you know, if we just think about the orbitals coming together just the way they are, we really wouldn't predict the sort of bond angles that we do see when we do see these molecules, and we talked about in the geometry part. And that's because if you kind of think about it, for example, if you take an s orbital and you take sort of a p orbital, in theory, they're sort of different shapes, if you will. There are also different energy sort of levels as well. And what would happen if you try to sort of mix those guys together, we would expect probably some different sort of bond angles than is what is observed with these molecules. So to sort of help us try to figure out why we do see these bond angles associated with these molecules, they came up with this idea of hybridization. And really the idea of hybridization is that we make these hybrid orbitals. And basically what happens when we sort of mix an s orbital and a p orbital together is we end up getting two orbitals that are exactly the same in shape. And they also end up being really the same in energy, which allows for sort of better bonding to occur than you would if you just sort of slap together an s orbital and a p orbital together. So the idea of hybridization is just that we take the atomic orbitals, and atomic orbitals again are our s's or p's or d's that we've seen before, and we basically mix them together. And what comes out is this hybrid orbital, which is sort of a mixture of both of those guys together. But sort of the benefit of it is these hybrid orbitals, as it says here, ends up being the same shape, and they end up being sort of exactly at the same sort of energy level as each other. And again, that allows for better interaction of these orbitals when they do come together and better bonding to occur. So a couple important things about hybrid orbitals is the number of hybrid orbitals that we actually do get when it goes through hybridization is equal to the number of atomic orbitals that are involved. So what that means is if we take a s orbital and we take a p orbital and we mix these two together, that is going to give us 1 and 2, what are referred to as sp orbitals. So here we mixed two atomic orbitals, and what we produced are two hybrid orbitals over here. And again, we'll see a little picture of sort of their shapes, but they are kind of, in theory, the same sort of shape. They're also perfectly dead equal in terms of energy as well with each other. So again, that's going to allow those guys really to come together much better and interact much better than trying to take an s orbital a little bit lower in energy and a p orbital that has sort of a different shape and just kind of sticking those guys together. So let's talk about the simplest type of hybrid orbital you could have, which is the one I just described there, and that is what is known as an sp hybrid orbital. And in an sp hybrid orbital, as I just mentioned, we're essentially taking one s orbital and one p orbital, and we're mixing them together. So if you just kind of think about it, we have an s orbitals, p orbitals, there are 4 of them, or 3 of them. And, we have some d orbitals we might get into. So what we're going to be doing is, again, basically grabbing an s orbital and a p orbital. So we're mixing together two atomic orbitals. So the s orbital is this kind of circle red guy here, p orbital this kind of purple blue guy over there, that figure 8. And when they come together, a little hard to see here, but you get these two sort of lobes, if you will, and they basically look the same here, one on this side and one on this side. And these are our two hybrid orbitals that have been made. So in this case, we will get two sp hybrid orbitals that have been made. Again, the benefit of that is that they both have the exact same energy. They both have the exact same sort of shape as well. So let's take a look at an example of that. By the way, this bond angle in this hybrid orbital is 180 degrees. So something that relates to hybrid orbitals is, if you remember our electron pair geometry, something with 2 electron pairs is basically what we just did here, has a electron pair geometry of linear and a bond angle of 180 degrees. So the electron pair geometry that goes with sp hybridization is linear. And again, it gives you that 180 degree difference between them. So if we look at an example here, this is BeF2, this is an exception to the octet rule. This is a incomplete octet. And again, if we draw this guy here, if I could hit the right thing on my thing. There you go. Maybe move some things around. And if we draw this, this is what it looks like right here, BeF2. And if you weren't sure it's going to be sp hybridization, let me show you exactly how you figure it out. From the Lewis structure, you go 1 electron pair, 2 electron pairs. And basically, you could simply count off what that means. And what I mean by that is you always start with the S. So 1 and 2, that means it's going to be 1s, and p hybridization, this will be sp hybridization that's going to go on here. So if we look at beryllium, and beryllium's electron configuration here is 1s2, 2s2. It has 2 valence electrons. These 2 valence electrons are these guys right here. So this is, again, beryllium's orbital diagram here. What's going to happen as these guys go through hybridization is you're always going to get this promotion. So one of these electrons in the lower energy level is going to work its way up to the higher energy level. And what you'll now have is an electron in a p orbital, and you'll have an electron in an s orbital. And these are the 2 atomic orbitals that are going to come together to make our 2 sp hybrid orbitals. And what's going to happen in this case is each one of these hybrid orbitals has the ability to make a bond, right? It only has 1 electron each. So this guy, for example, will go and make a bond with a fluorine. This guy over here will go and make a bond with a fluorine, and that would account for the bonding that we see here in BeF2. Question on that. So the simplest way to sort of identify hybridization, if you have your Lewis structure, is really to count electron pairs. And what you want to count is the same way as you would count in something when you're doing geometry, which means if you come across a double bond or a triple bond, it would still count as 1. So when you're doing sort of hybridization, that's the same way you kind of want to count up electron pairs. The next sort of hybridization is sp2 hybridization. And much like the name implies, we're going to take an s orbital and we're going to take 2 p orbitals, which you can kind of see here. Again, the red circle is our s orbital. This guy right around here is 1 p orbital. And I'll just kind of point it out over here. That is our 2nd p orbital. And that's going to give us 3 hybrid orbitals. And it's going to give us 3 hybrid orbitals because we took an S, a P, and a 2. And that is 3. So we get 3 hybrid orbitals that basically occur. They look kind of like these guys. Again, they're going to be equal in energy, also equal in shape. And you could kind of see the triangle type formation here. It has a bond angle of 120 degrees. sp2 is 3 orbitals. And if you think about electron pair geometry that we talked about, something with 3 electron pairs is our trigonal planar geometry. So our trigonal planar geometry will have sp2 hybridization going on, basically 3 electron pairs, and same idea. Sometimes people get really confused about how to figure out hybridization, and really just kind of counting them off is a good way of going. And again, we have 1, 2, 3 electron pairs. And if you just put a circle around it, that is an S and 2 P's. So that tells you your hybridization, just like that, sp2 hybridization that's going to go on here. So let's take a look at an example of that. And if we do, we could look at BF3, which again is also an incomplete octet. And if we draw BF3, again, it looks like this. And again, 1, 2, 3 electron pairs. And like I said before, really the easiest way to figure out hybridization is just to do this. Like I just did on the previous page, 1, 2, 3. So I took an S and 2 P's. So I know this is going to be sp2 hybridization. What we're looking at here is boron's electrons. Boron is 5, which is 1s2, 2s2, 2p1. It has 3 valence electrons, which are these guys, and it has 2 valence electrons here and 1 here. Same thing's going to happen as this goes through hybridization. This lower electron will work its way up just like normal and go to the box next to it. Then this 1s orbital here and these 2 p orbitals here going to go through our hybridization, and we're going to get 3 sp2 hybrid orbitals. We also see that we also are left with 1 unhybridized orbital over here. So 1 unhybridized p orbital does get left just alone, and that's going to be really important a little bit later on when we talk about kind of double bonds and triple bonds, having that sort of extra unhybridized p orbital. Same idea here with our boron. Each of those borons now have an electron sitting in them, which means each of these borons now can make a bond to fluorine. Right, so it's going to lay up a bond basically to fluorine in each of those, and that would be our sp2 hybridization. Any questions on that so far? That then takes us to sp3 hybridization. And sp3 hybridization, again, much like the name implies, is when we take 1 s orbital and all 3 p orbitals and basically hybridize them together. So if you just count the letters, 1 s and 3 p's, that is 4. So that's basically like 4 electron pairs. And again, you can see you get 1, 2, 3, and 4 hybrid orbitals happening. And something with 4 electron pairs is our tetrahedral geometry. And this guy also has a bond angle of 109.5 degrees, which is our tetrahedral bond angle happening here. So when you have 4 electron pairs, just like you would count for geometry, you would expect this guy to go through sp3 hybridization. And again, let's take a look at an example of that, and that would be CH4. So same idea here. If we drew CH4, one, two, three, 4 electron pairs. And if you were trying to figure it out just from scratch, like I've done on the previous ones, just set your thing up just like this and go an S, a 1, 2, 3, and 4. And now I have going to take all those guys to be hybridized. I took an S and 3 P's, gives me sp3 hybridization. That's going to happen in this case. We are again looking at carbon down here in terms of its electrons. Carbon, which is 6, has an electron configuration 1s2, 2s2, 2p2, and these are the 4 valence electrons in carbon. Same thing's going to happen. We're going to get a promotion of that lower electron, going to find the empty orbital up here, and then this s orbital and all 3 of those p orbitals are going to come together to make our 4 hybrid orbitals for carbon. Each of these are missing an electron, which means they are able to bond, and each of these would make a bond with a hydrogen in our CH4 here, basically. So sp3 hybridization goes with basically tetrahedral electron pair geometry, and that's basically the way you could sort of identify it. Question on that there. Now, if we look at something, say, like, let's take a look at, take a look at water, for example. Actually, let's take a look at NH3 first, I think, which I think is a little bit further down on your page. So if we look at something like NH3, and we draw NH3, looks something like this. And this is probably how you would probably have something to identify hybridization for. So if you were to identify the hybridization, take a moment and think of what the hybridization would be here. So the hybridization hopefully is what you want to do is count it just like you were doing geometry. And what that means is I have 1 electron pair, 2 electron pairs, 3 electron pairs, and my single bond electrons up here gives me 4 electron pairs. And if you're not sure what the hybridization would be, you've got 1, 2, 3, and 4 electron pairs. If you just put a box around all those things, you took an S and 3 P's together. So the hybridization of this guy is sp3. And if we look at nitrogen, which is 7, 1s2, 2s2, 2p3, these are the 5 valence electrons that are in nitrogen. So if we kind of do our little orientation here like we were doing, we have our 2s, which has a couple of electrons. We have our 2p, which has 1 electron, 2 electron, and 3 electrons happening. And again, this is nitrogen down here. And what's going to happen as it goes through hybridization, we are going to get that electron coming up from the lower energy level. So this guy is going to come up. And when he comes up, just like we talked about with electron configuration, he's going to go into here at this point. And what that's going to do is give you 2 electrons in that box and an electron in each of these other boxes here. And this is my 2p. And then down here, my 2s has the 1 electron. At this point, it's going to take everybody that's here to go through hybridization because we have already identified it as being sp3. And because we are hybridizing 1, 2, 3, 4 atomic orbitals, what we will end up with is 4 equivalent sp3 hybrid orbitals, where it will look something like this. And again, these are the hybrid orbitals on nitrogen we're looking at this point. So if you want to kind of think about what is going on in terms of the bonds and everything that's happening, let's just call this guy right here number 1. So that is a bond between a nitrogen and a hydrogen. So we'll just use this box here. That is going to make a bond between a hydrogen and a nitrogen. That would be bond number 1. This guy over here we'll just call bond number 2. That also is going to be a bond between nitrogen and hydrogen, which would be bond number 2. This bond up here would be bond number 3, also between a nitrogen and a hydrogen. And now if we look at our Lewis structure, the only thing we have left is these 2 non-bonding electrons. They're sitting on the nitrogen, and looky there, we have a box that has 2 electrons, and these would be the lone pairs on the nitrogen that are there. So this really accounts for all the bonds that we see. It also accounts for the non-bonding electrons that we see. And we could even get extremely specific here. We could say that each of these bonds is a bond between the sp3 hybrid orbital in nitrogen and the 1s orbital in hydrogen. Hydrogen will not go through hybridization because it only has 1 electron, so it will not go through hybridization. So hydrogen has a 1s1 electron configuration. So we know that this is a bond between sp3 hybrid orbital nitrogen and a bond between the 1s orbital in hydrogen. Question on that there. And again, even though they're not all bonds, it still has the 4 electron pairs. So this is why when we think about geometry and hybridization, we're thinking about the electron pair geometry. Again, we just want to count the total number of electron pairs. Does not have to be bonds. Any questions on that particular one there? We could also see something similar. For example, if we look at water, and if we look at water, which is H2O, I think still. So if we look at H2O and we draw H2O, And if we do this and we look at it, we got 1 electron pair, 2 electron pairs, 3 electron pairs, 4 electron pairs in this case. And again, if you're not sure what the hybridization of this guy is based on your Lewis structure, you always start at the S. So I got 1 electron pair, 2 electron pairs, 3 electron pairs, and 4 electron pairs. And if I add up everything I just put an X on, I also, for this guy, get sp3 hybridization happening for my oxygen. So if we look at oxygen, which is 8, looks like 1s2, 2s2, 2p4, oxygen has got 6 valence electrons happening. So if we just kind of draw what is going on, like we've been seeing here, we have a 2s that's got a couple of electrons. We have our 3 boxes for our 2p. And there's 4 electrons, which means 1 at a time. And then we would come back and fill it up. And again, this is for our oxygen we're looking at. Same thing's going to happen when it goes through hybridization. This electron is going to go up. And when it goes up, it's going to fill our normal box, which would be our middle box there. And that would give us these guys filled like so for our 2p. And our S on the bottom will now just have 1. And since we did identify it as sp3 hybridization, everybody's going for the ride here. We're going to take all 4 of them. And that's going to give us, just like we talked about before, 4 equal hybrid orbitals that are equal in size and shape, equal in energy. And if we kind of fill in what we got going, we got something like this. And these would be 4 sp3 hybrid orbitals, again, for our oxygen. So if we want to sort of figure out, again, what's happening here with everybody that's present, we'll make this guy right here bond number 1 between the oxygen and the hydrogen. This oxygen can do that bond since it only has 1 electron. We also have a second oxygen-hydrogen bond. It could be like here. And at that point, what we are left with is an electron pair on oxygen and another non-bonding electron pair on oxygen. And that is what these 2 represent here. These are the 2 lone pairs that we see on oxygen that was already filled out. So hybridization here, again, adequately describes what we see in our Lewis structure in terms of non-bonding electrons, in terms of bonds that are happening here. And again, we could describe the bond between the oxygen and the hydrogen as the oxygen being an sp3 hybrid orbital bonding to a 1s orbital in hydrogen in this case when they do come together. Questions on that there? All right. So sort of wrote all over it. That was good. All right. So, I guess it's good at what I drew was kind of like what's on the page, I suppose. Let me get rid of what's on the page so I can see it, I suppose. All right. All right, we can see it. That's good. All right. So in general, as I talked about, as we just saw in those 2 examples that I just did, even though there's non-bonding electrons involved, you still want to count those and apply hybridization to them. So our hybrid orbitals can contain basically our non-bonding electrons or our lone pairs that are on the central atom, as we saw with our NH3. We had the 1 hybrid orbital that had the 2 electrons in it. And then for our H2O, as we just did there, we had the 2 hybrid orbitals that both had a pair of electrons. Now, when we talk about bonds that are happening, there's a couple different types of bonds that we come across, and one's what is referred to as a sigma bond. So a sigma bond is basically a bond that occurs when an orbital and an orbital pretty much go head on. So they head right at each other. They basically overlap, come straight at each other, and get head on overlapping that it occurs. And that is what is referred to as a sigma bond. Really, the easiest way to figure out if something is a sigma bond or not is, this might not be 100% scientifically correct, but you know, it's actually right, I think. So it's basically every single bond that you make is a sigma bond. Yeah. So when you're drawing a Lewis structure, for example, like the CH4 that we had, this guy has 1, 2, 3, 4 sigma bonds. Yeah, so they're all sigma bonds. H2O, as we just saw, has 1, 2 sigma bonds pretty much. So every sort of, the way I sort of remember it is when you're drawing your Lewis structure, every time you just lay up a single bond, it's a sigma bond pretty much. And those orbitals are basically, what that means is going to come straight at each other, and you're going to get that area of overlap that's going to basically occur. So hybrid atomic orbitals result in really stronger bonds than unhybridized orbitals. And again, it really does account for a lot of the geometry that we see and the bond angles that we see when we think about those different sort of electron pair geometries. So this is NH3, which we did just a second ago. So in case you missed what I erased, that it is right there. Again, going to be able to make those sigma bonds, and a hybrid orbital that has those lone pairs. Again, this would be our nitrogen lone pairs, and each of these would make a sigma bond with hydrogen. Now, what happens when we start to get some multiple bonds that happen? We do have some unhybridized orbitals that get in play when we get into double bonds or triple bonds that are happening. And we create another type of bond, which is referred to as a pi bond. And a pi bond is the formation really of when we make a double bond or a triple bond is basically what happens. So let me just kind of get one here, and we'll take a look at one maybe here. So for example, let's take a look at, let's do this guy here. Okay, so we got a couple of center atoms here. We got a carbon on the left, carbon on the right. And if we wanted to do the hybridization of each, we could do the hybridization of each by basically putting our hand over one half of it and looking at the other half. So I'm going to call this carbon number 1. I'm going to call this carbon number 2. So I'm going to give you a minute or so here. For each of those carbons, carbon 1 and 2, figure out the hybridization of those guys. So again, when you're counting stuff like we talked about double bonds and triple bonds, just like you would count up electron pair geometry. And in this case, since there is basically two sides, put your hand over one side and then move it over and put your hand over the other side. Okay, so let's take a look. If we want to assign hybridization, I'm going to start with carbon 1. So this is 1 electron pair here. This is 2 electron pairs here. And we would put our hand over carbon 2 side, but we would still count this, which would count as 1 electron pair, 2 electron pairs, and our double bond would count as only 1 more electron pair. So that is basically 3 electron pairs on that guy. Same thing is going to happen for carbon number 2. This is going to be 1 electron pair, 2 electron pairs, and our double bond is going to count as 1 more electron pair. So carbon number 2 also has 3 electron pairs. So if I want to identify the hybridization, again, you could just do this simple sort of thing to count it off, which is sometimes easier for people. I got 3 electron pairs, so starting at S, 1, 2, and 3 electron pairs. That means I just did an S and 2 Ps, which means the hybridization of carbon number 2 is sp2. Hybridization of carbon number 1 is also sp2. By the way, the geometry of both of those carbons would both be trigonal planar. They would both be trigonal planar. When you have more than one central atom and you need to do geometry for each one, you just do them separately. So hand over one side and then move it to the other side. First off, any questions on how to figure out the hybridization part of it? All right, so we're going to focus on the carbons first here. And the carbon's electron configuration, 1s2, 2s2, 2p2, carbon having 4 valence electrons to begin with. Now, since carbon is going to be sp2 in this case, this is what it's going to look like before it does any hybridization. If I draw it a little bit better, we have basically 2 electrons in the 2s and 1 electron each into the p. As it goes through hybridization, this electron is going to go up to our empty spot here, and we're going to get an electron in each of these 2p orbitals, and we will have still 1 electron in our 2s orbital. And now it's ready to go through hybridization. And when it goes through hybridization, since we've already identified it as being sp2 hybridization, we're going to take our s orbital, and only 2 of these p orbitals is going to go through hybridization. And because we took 3 of those orbitals, we are going to get 3 equal sp2 hybrid orbitals, where each of them has an electron. But in addition to that, we have one of these p orbitals here that was not hybridized. So we also have a unhybridized p orbital. Any questions on that so far there? Okay, so what I'm going to do is, because both carbons are exactly the same, they both will go through the exact same hybridization, they're both going to end up with this exact same arrangement here. So I'm just going to redraw it over here. So one carbon will have our sp2 with an electron in each. We'll call it carbon 1. We also have that unhybridized p orbital up here. We will also have carbon number 2, which pretty much got the same arrangement. And this would be carbon number 2. All right. So what I'm going to do now, see there, just so you can see that everything gets accounted for. In addition to the 2 carbons, we have 4 hydrogens, right? So we have basically 2 hydrogens on each side. So I'm just going to draw my hydrogen here, which would be a 1s orbital, and my hydrogen, which would be a 1s orbital over here. And I'll squeeze my hydrogen over here with a 1s orbital. And again, hydrogen will not go through hybridization because it only has 1 electron, so it cannot go through hybridization. So this is basically everything we got going on in terms of our structure here. So let me just get some room so we can clear it up a little bit here. Okay. So if I look at my structure originally, let us start sort of accounting for everything that we got going on. We have bond number 1 over here, which is between carbon and hydrogen. So this is a carbon on number 1. This is C1, and this is C2. It can make its bond here. And that's basically one line or a single bond. So this is a sigma bond. So that's one sigma bond right there between the carbon and hydrogen that's happening. We also have a similar bond happening between the carbon and the other hydrogen. So we'll just call it this one right here, which would be bond 1. That'll be bond 2, also going to be a sigma bond. So there's our 2 sigma bonds between the carbon and the hydrogen on the first carbon. We have the identical thing happening on the second carbon. So number 3, bond right here. Also a sigma bond happening. We have number 4 right here coming this way. Also a sigma bond. So I've accounted for basically 4 of my 6 bonds. What I have left is a double bond, right? So I got a double bond happening. So one of these bonds, one of the lines in the double bond, like the first line in the double bond, is also going to be a sigma bond. And it's going to be a sigma bond between the 2 carbons. So these 2 guys that are left. So I'll just call this number 5. Number 5 will also be a sigma bond that's happening. Now, a sigma bond in this guy, we have 5 of them, but now we have a second line that makes the double bond. And the double bond, as you can see, cannot be made up of any of our hybrid orbitals. We basically accounted for all the electrons in our hybrid orbitals. So what happens when we make that 6 bond here, that is what is known as a pi bond. And a pi bond happens from the only 2 electrons that are left, and that is the 2 unhybridized p orbitals here. So these 2 unhybridized p orbitals makes bond number 6, and this is what is known as a pi bond. So this is a pi bond between the 2 unhybridized p orbitals, and you could even be super specific as to which orbital it is, because if you remember when we talked about electron configuration, this guy would be the 2px orbital, this would be the 2py orbital, and this last one over here that was unhybridized is the 2pz orbital. So this is actually a pi bond between the 2 unhybridized 2pz orbitals is basically what is happening there. And that accounts for all 6 of the bonds. We can see we used up all of our electrons when we did this. Now you may be asking, what is the difference between, say, a pi bond and a sigma bond? Or you may not be asking that and may be asking, is this almost over, this lecture? Which I might be asking that myself, but who knows, we'll see. But the difference is a sigma bond, as we talked about, is when the 2 orbitals basically head straight at each other, head to head, and they overlap like that. What happens in a pi bond is, because these are unhybridized p orbitals, they look just like regular p orbitals. And unhybridized p orbitals are that figure 8 type of shape, right? So what we get when we make actual pi bond is not head-to-head overlap like we get with a sigma bond. It is what is referred to as side-to-side overlap between these 2 unhybridized p orbitals. This is what is referred to as side-by-side overlap. Above and below, kind of the plane of the bond, the bond would be kind of here in this area. So we get this overlap that happens above and below the plane of the molecule. And again, that is what is referred to as a pi bond. Any questions on that there?
Yeah, I had a question.
Yeah.
So will there ever be a time where we have the 2pz unhybridized and they're creating those pi bonds?
Yeah.
Will we ever have like 2px be unhybridized and also have hybridization taking place?
You most likely will not necessarily have the 2px. You can have the 2py, and that will happen with like a triple bond, which we'll look at next. But probably you won't get to that because basically you can make a single bond, double bond, or triple bond. So what happens when we get a triple bond is you end up with 2 unhybridized p orbitals, and that's most likely going to be the py and pz that are unhybridized in most cases.
Got it. Thank you.
Yep. Other questions? Okay, so let's take a look at sort of that question and sort of what happens on that. So if we take a look at a triple bond, when we look at this triple bond, again, we have these 2 carbons here, carbon 1 and carbon 2. And if we assign hybridization for carbon 1 and carbon 2, I'll give you a second. You assign the hybridization for each of those carbons, and then we'll talk about sort of what happens with it. Okay, so again, when you have multiple center atoms, you can just kind of put your hand over one of the atoms, like the C2, and the bond that's going into the C2 still counts. So electron pairs for our first carbon, one electron pair here. And again, this triple bond, even though it's a triple bond, just like you do with geometry, will only count as 2. And so it basically has 2 electron pairs. And so does the other carbon, 1 electron pair here. And again, our triple bond only going to count as 1. So if you just have the Lewis structure and you need to figure it out, just go just like this. And I have 1 electron pair, 2 electron pairs. So that tells me I have an S and a P. So the hybridization of both of these carbons are actually going to be sp hybridization by looking at it. And what that means is when we look at carbon's electron configuration, like we saw earlier, with its 4 electrons, what's going to happen is we are again going to get that promotion up to the 2p, and we will end up with an electron in each of the 2p orbitals. We will have 1 electron in the 2s orbital. And because we identify this as sp hybridization, we're just going to hybridize 1 of each of these guys. And because we hybridize only 1 of each, that will give us 2 equivalent sp hybrid orbitals, each with an electron in it. And now in this case, what we're left with is 2 unhybridized p orbitals that both have an electron in it. And this is basically the same for both carbons. So to answer your earlier question, Austin, this would technically be your 2py, right? And your 2pz orbital that didn't get hybridized. And both carbons will basically end up this exact same way. So if we kind of arrange it like we did before, I'm just going to erase some stuff here so I could get things in here, I think. Actually, we'll just do it down here. So we will have for 1 carbon, carbon number 1, 2 sp hybrid orbitals. They're both sp. We will also have our 2 unhybridized 2p orbitals. And carbon number 2 will do the same thing. It will have its 2 sp orbitals and its 2 unhybridized 2p orbitals. And again, if we just sort of count up everything, we basically have 1 hydrogen on each side going to make a bond. So we have a hydrogen over here, which is an electron, which is 1s, and we got like a hydrogen over here with a 1s electron. So if we keep track of all of our bonds here, this guy being number 1 would be between the carbon and the hydrogen. And that is just a single bond, so that is a sigma bond that's happening there. We also, on the other side, have a bond between that carbon and hydrogen, which would be these 2 guys. And that would be bond number 2, which is again also a single bond or a sigma bond. Now we have really the triple bond that's left in the middle. So we got basically this triple bond left in the middle. The very first line, if you will, for the triple bond, we'll call it number 3 here, is going to be this sigma bond that's going to occur between the 2 carbons. So that would be bond number 3, which would be our sigma bond. We now have kind of like the double bond out of the triple bond left. And that double bond is going to be the 4th bond. And that is going to be an unhybridized p orbital and another unhybridized p orbital. Going to make our pi bond, and that would be bond number 4. Probably should have laid it up there. That probably would have been better. So we have that to that. And then we have the third bond in our triple bond, which would be bond number 5. And that works out nicely because we have an electron here and an electron here that can make the 5th bond. And this is also known as a pi bond as well. So in a triple bond, you have it made up of 1 sigma bond, which is head-to-head overlap of those orbitals, and 2 pi bonds, which is side-to-side overlap that occurs. And I will apologize in advance for my really crappy drawing right here, but I'll give it the old college try. So you have, for that second bond in the triple bond, an unhybridized p orbital that is going to do sideways overlap. And that would account for, say, the second bond here, the pi bond. And then we obviously have the pz and the px orbital available to us. So at a sort of a different angle, and again, this is where I apologize for my bad drawing, we also have those guys doing sideways overlap as well to make the kind of third bond, if you will. And in between, we have the sigma bond that's sort of happening. So we have, for a triple bond, it is composed of basically 2 pi bonds and a sigma bond. A double bond is composed of a sigma bond and a pi bond. Questions on that there? So let me just write that out so everybody can see it, I think. I'll write it here, I think. So basically a single bond, every single bond, the first line you draw in your Lewis structure, sigma bond, yeah. A double bond, which is consisting of 2 lines, basically. First line is a sigma bond. Second line is a pi bond. And your triple bond, which is basically 3 lines. First line is a sigma bond. Second one's a pi bond. And third one is a pi bond that's happening there. Question on that there?
So now I'm kind of having like a question about the shape.
Yeah.
When we're finding when you're drawing these figure 8s,
Yeah.
and they're in like different different like orientations.
Yeah.
Is that the orbital shape for the entire compound, or is that just for the non-hybridized?
Technically, it's the, well, technically speaking, they really don't have shapes. They're just theoretical sort of shapes. But the shapes that we associate with a p orbital, technically speaking, is for that 2p subshell in this case, the unhybridized orbital in that 2p subshell on like the second energy level, basically. Remember, they all have these other electrons right there, non-vol embodying the core electrons. So we're just looking at the valence electrons. So in the case of these examples, it'd be like the 2p subshell in that sort of orientation of where it is. And that's where the 2p or any p ones have the x, y, and sort of z in 3-dimensional space. And that's how come they're kind of at different angles and stuff like that when you draw them.
So are the sigma bonds just more like covalent?
Yeah, they're all technically kind of covalent bonds. It's just different ways the orbitals come together. So the main difference between sort of a sigma bond is when you have these orbitals, be it like s orbitals or hybrid orbitals, whatever it may be, they basically come together. They just shoot right at each other head on, right? In the line of the bond, basically. They just go right at each other. The difference is, if you sort of imagine the bonding sort of plane right there, when you have these unhybridized p orbitals, they tend to do not right at each other, but sort of overlap above and below the plane of sort of the bond in sort of 3-dimensional space. And it gets a sideways overlap, which is your pi bonds rather than your sigma bonds. Well, I'll terribly draw it, but you got like your sigma bond happening kind of there, yeah. And that'd be kind of like your double bond, even though it kind of looks like 3 bonds happening. But this whole thing is considered 1 bond, 1 pi bond. And then this would be like your sigma bond. And then again, I won't be able to draw it very well, but at a different angle, you have that second unhybridized p orbital which also doing that.
That would be one more pi bond.
One more pi bond, kind of sandwiching it
That
all.
makes total sense. Okay, thank you. That totally answers my question.
Okay. Other questions on that? Okay. So let's see. We've got that one. Now we can also apply hybridization to everybody's favorite thing, which is those expanded octets. And in those expanded octets, we get into the Ds, right? And that's with our trigonal bipyramidal and our octahedral. So again, you could kind of look at it the same way. If you just kind of count everything going on here. If I needed to go 1 electron pair, 2 electron pairs, 3 electron pairs, 4 electron pairs, 5 electron pairs, that is going to be my sp3d. That is our triangular bipyramidal that we talked about with geometry, our 5 electron pairs. And if we went to 6 electron pairs, you could count the same way, starting at the bottom there. And you would have 1, 2, 3, 4, 5, and 6, which would get you sp3d2, which would cover your octahedral or expanded octet in terms of its geometry as well. So we definitely can reach in there and pick those guys off. Any questions on that there? All right, so now most people at this point are like, do I have to do all those arrows and stuff like that? And the answer is, probably not. So it's just to help you better understand what's going on, or maybe not help you understand what's going on better. So let's take a look at some things just to show you really how fast you could probably figure out what's going on here. So let's just do this here. Let's take this guy here. And let's do this guy here. And let's do this guy here. So I tell you what, for each of these carbons, carbon 1, carbon 2, carbon 3, and why not, let's do this guy as well, this fourth guy. Give me the hybridization of each of those. And then also how many total sigma bonds and pi bonds are there in that molecule. And then for this guy here, give me the hybridization of each of these guys and how many sigma and pi bonds in the whole thing. And lastly, same deal here, give me the hybridization for these guys and same idea, how many sigma and pi bonds are there. And again, do it without drawing arrows or anything like that. You should be able to actually just look at the Lewis structure and figure that out pretty quickly. So take a few minutes to see what you come up with, and then we'll talk about it.
So just to clarify, we count non-bonding electrons, but they're
Yes.
non-bonding, right? So they don't count as a sigma or a pi bond.
Yeah, so the non-bonding electrons obviously wouldn't be any type of bond, but you do need to count them just like you would do with geometry. So you're looking for total electron pairs. And again, as you're counting them, double bonds or triple bonds count as only one electron pair. Okay, let's start looking at it. So see how we're doing. Let's go. All right, we'll start with the first carbon here on the top. Again, I'm going to go with the hybridization first. So I got 1 electron pair, 2 electron pairs, 3 electron pairs, 4 electron pairs. So again, 1, 2, 3, 4. That tells me that is sp3 hybridization. When I go to carbon number 2, I got 1 electron pair, 2 electron pairs, 3 electron pairs, 4 electron pairs. Going to be the same. 1, 2, 3, and 4 tells me this guy also is sp3. When I get to carbon number 3, I got 1 electron pair, 2 electron pairs. Double bond here counts as only 1 electron pair. So that is 3 electron pairs for that carbon. And that would be 1, 2, and 3 only. So that is a S and 2 P's in that particular case. And lastly, if we look at the oxygen, which you can apply hybridization to outside guys sometimes, this is 1 electron pair for our double bond, 2 electron pairs, and 3 electron pairs. Again, 1, 2, 3, gonna also be sp2. Any questions on how do I sign that hybridization? Okay.
How would you figure out geometry? Do we do geometry for each part?
You would. So in this case, I wish I could put my hand over the screen, but I'll just put a virtual box. So what you would do for carbon number 1 is basically right here, just ignore everything to the right. And you would do the 4 bonds that you have there. So 4 electron pairs and 4 bonds would be tetrahedral for the molecular geometry. Then you would move to the guy in the middle and pretty much ignore both sides. And he also would have 4 electron pairs and 4 bonds. He would be tetrahedral. And then the guy on the far right, you would ignore everything to the left. He would have 3 electron pairs and 3 bonds. He would be trigonal planar. So basically, put your hand over the half of the molecule that you're really not looking at, but the bond and electrons that go into that part you have your hand over, you still count. So you would have 3 different geometries for this guy because there's technically 3 different central atoms. Other questions on that? So let's take a look then at sigma bonds. So sigma bonds are essentially in a Lewis structure every individual line. So that's a sigma bond. That's 1, that's 2, that's 3, that's 4, that's 5, that's 6, that's 7. And remember, our double bond is made up of a sigma bond. So Is that 8? 1, 2, 3, 4, 5, 6, 7, 8. I think I missed one down here, maybe 9. 1, 2, 3, 4, 5, 6, 7, 8. I can't count right now. 1, 2, 3,
It's
9.
eight.
Is it 9? 9, I think, right? One more time. 1, count with me. 2, 3, 4, 5. I think I missed that one earlier. 6, 7, 8, and 9 sigma bonds, looks like. Next week, we'll do the alphabet. There we go. 9 sigma bonds. There we go. And then obviously our double bond is made up of a sigma bond, which we already counted, and also a pi bond, which would be like this guy here, right? So it would be 1 pi bond total in that case. Question on that there. All right, let's take a look at the other ones that we got going on. So we'll start with hybridization. We'll start with our outside oxygen here. So 1 electron pair, 2 electron pair, again, double bond, only counting as 1. So that is 3. So that should be sp2 hybridization. Guy on the right is going to end up being the same because he's identical. Our center carbon would have 1 electron pair on the right and 1 electron pair on the left. And that is only 2. So an S and a P in that case, he would be sp hybridized. Question on those there. And in terms of sigma bonds, I got a sigma bond there, part of my double bond, and I got another sigma bond right there. So this guy would have 2 sigma bonds total. He would also then have 2 pi bonds as well. Question on that one there. And lastly here, carbon, 1 electron pair, triple bond, only counted as 1. That is 2, which means he has sp hybridization. The nitrogen has an electron pair on the dots and also just 1 counting there for the triple bond, also only 2. So an S and a P would give us the hybridization. And in terms of sigma bonds, we'll go with the green I already did. 1 sigma bond there, 2 sigma bonds there. And then we also have 2 more lines there in our triple bond, which would get us a pi bond there and a pi bond there. And that looks like 2 pi bonds. Any questions on how to identify hybridization, sigma, pi bonds? As you can see, you don't have to draw all those arrows and stuff like I did previously. You could just keep it very simple. Just count up electron pairs. Doesn't matter if they're bonds or dots. You want to count up the total number of electron pairs, just like you do with geometry. Double bond, triple bond counts as 1 electron pair. And as I did there on the right, you could just kind of count it off and figure out how many orbitals you did, and that will give you your hybridization. Any questions on that fun stuff there?
Are both of those linear?
Yeah, so CO2 there would have basically 2 electron pairs on that carbon and 2 bonds, which would be linear. And that does go with the sp hybridization as we talked about, right? So that all makes sense. And then our HCN there, the carbon in the middle, would also have 2 electron pairs and 2 bonds, which also goes with our sp, and it would be linear as well. Yeah, so again, remember that these go with sort of that geometry. The electron pair geometry matches up, but the molecular geometry on those 2 bottom ones would be linear. Other questions? All right, so wrap that up for today. So the exam is what's left. It will open at about 7:15, the start of lab. You need to have, your proctorial, your camera that shows to the best of your ability you and your work area, like your papers and that type of stuff, the best you could do. Got a laptop, push it back a little bit, yes, or sit back from it, put it to the side, something like that, I'm not just looking at your hairline, yes, the top of your head or anything like that. So make sure you try to get as best you can with your equipment to show both your work area and obviously you. Again, it is closed book, no notes, nothing like that. Please don't have any of that out. It's going to require me to give you a 0. Yeah, so don't do anything dumb like that. Also, don't do anything other things dumb like your calculator shouldn't be out. No, I'm just kidding. You can have your calculator, but you should have your phone out. You shouldn't be texting people or anything like that during the exam. And a reminder that there are different versions and different questions. Just a reminder, don't have the right answers on the wrong version. Just like the quiz, the test, as I mentioned last time, the first part of the test is all multiple choice. So the right answer should be there somewhere. You do not have to show any work for that first part. The second part is labeled written part. And much like the quiz, there will be certain problems where you do need to upload your work and show your work that includes all the units, the setup, and everything like that. And then there will be some questions that are labeled you don't need to show work, which obviously you don't need to upload the work for those. Okay, so the test is kind of two parts like that. There's a periodic table attached there as a picture, and also one that you could download, and also some conversions will be on that as well. I think every conversion that you should need, I think, should be there. Other than that, remember that once you submit your exam, you're expected to immediately upload your work in a reasonable amount of time. Again, if it's uploaded way later than that, you're not going to get credit for those problems. So make sure that you do upload it in a timely fashion. Also, just like the quiz, you'll be able to see every question. Do not hit submit until you're all done with the exam, and submit it once. And once you start the exam, again, the timer will not stop, even if you click away or something like that. So make sure you're ready to take the exam. Remember that it will only be open for a window of time. I think it closes somewhere after 10 or something like that. But if you do not start around 7:15, you may run out of time, yes, and it may cut you off. So you are expected to start around 7:15. You don't have to start right at 7:15, but in that general ballpark, you should start, and you will not run out of time. I don't expect to see people starting it like at 8 o'clock, 8:30, or anything like that. A, you're going to run out of time, and B, that's way too late. So you are expected again to start around when it opens, and it will open about 7:15. There will be an announcement that will go out with a link to where you can find the exam, but just in case, you could find the exam in the module section. There's a whole module, just like the quiz, where you have to do the honesty agreement and all that good stuff, and then you could upload your stuff at the end. Any questions on any of that stuff there? Obviously, there is no lab today or meeting or anything like that, so all you're going to do is take the exam. I think everything should be pretty self-explanatory. I don't think you'll have any questions. If you do, you could email me, but I don't anticipate you probably will have too many questions or anything like that.
Professor,
Yeah,
what's the time limit on the exam?
I believe you have, I think you got 150 minutes, so that's 2.5 hours, which
Okay.
I think should be plenty of time. Probably more time than you need, but it should be plenty of time, I think. Yeah.
Okay, thank you.
Any other questions on that? Okay. So again, no lab today, and then we'll just pick up with lecture on Thursday. And like I said, if you do have some type of question, you could email me through Canvas, and I'll answer it if I can. Obviously, I can't tell you how to do anything, but I can answer it. Last thing I'll say is, like normal, make sure that you do read the instructions for every question as to how to properly answer it in Canvas, so that you do answer it correctly. And again, the score that you see at the end may not be your overall score until I kind of go back and look it over and stuff like that. Other than that, you should not be asked for any type of code. If you are, that means that you don't have Chrome, you're not using the proctorial extension and that type of stuff. So make sure you fix that. Other than that, make sure you put here in the chat, good luck on your exam and all that good stuff. And I will see you on Thursday, I think. Yeah.
Thank you, Professor.
Thanks. Have a